Hey guys, welcome to this week's section. It's amazing to see such great attendance this time. We've doubled our attendance numbers, which is great to see. So today is going to be an interesting section because this week we went over the ethical coursework and we saw some optional items in proofs, and we went over, we have the option of going over COC, COQ, as well as other things. But before the section started, I asked you guys what would you guys like to do during this week's section, and you guys indicated that you want to go over the homework 5, and go over some of the problems, without giving the solutions, of course. So we can do just that. So let's start with question 1. I believe you said that you had a few questions about question 1. So yes, we can start. What would you like to go over?
So my understanding is question 1, you want to prove monad laws.
Yes.
So you just want to prove those like left unit, right unit, and associativity laws. So is it kind of just plugging in values? And how would you like formally do this? Is it just like a simple left side evaluates to right side?
Yeah,
thing?
for sure. So yes and no. So it's going to be a mix of what you said. Let's go to question 1 real quick. This is lecture. Okay, so this is the P set. The first question is where you're asked to prove the monad laws for left unit, right unit associativity right here. And so yeah, the way that you'll be going to prove this is proof by construction. So what I mean by proof by construction is, let's say for the first question, right, left unit, where you start with bind, parentheses, return xf, and then you're going to end up with fx. The way you're going to start this is by basically starting with what you have. And to prove left unit, you're going to start from here, and you're going to aim to end at this point right here. Yeah, so the way you do that is you say, okay, return x, f. You're going to do some intermediate steps where you're going to end up with fx. And the way that you do these intermediate steps is by using the definitions that are given in the first part of the homework. Yeah, exactly. So, yeah, for writer, which is right here. Yes?
While doing the proof by construction, while going from one step to the other, I indicated which rules I am using by parentheses between separate lines. Is that okay?
Yeah, that should be fine. As long as you indicate which definition you're using to go from one step to another, that should be fine. So we can just start this question even, like when you do bind return xf, if you guys looked at the problem, what is like the first logical step that you would take from here when you look at bind return xf?
Instead of return x, write what the return x does.
What does it do?
Which is like writer x, comma, mmt.
Exactly. So yeah, you just write bind. And why did you do this? So like why, what made you think of doing this step?
Because return x is defined for writer.
Right.
When an x structure.
Right. MT. Exactly. And what was this the definition of? Like what did we replace here?
Return.
Return. So yeah, all you also have to do is just write definition of return. Yeah. And then yes, you're going to be doing similar steps down here. You probably want to use the other definitions given to you, such as bind, substitute, left unit, right unit, monoid loss, and obviously substitute at the end. And that should give you the answer for that first question. Yeah, so let me ask you guys a question. What does MMT represent? Right here, the keyword. MMT, what does MMT represent? Unit value, right? It's or it's like an empty list, basically. Yeah. Yeah, then what does X represent here? Would you like to tell me?
I don't know. You can do the question without understanding what X is.
Right, exactly, but it's better if you understand. Yes. So X is basically like a value that's storing in writer. You're given a tuple, right? The writer monad, comes with obviously its type, which is writer, and then you're given a tuple x and MMT. And you're basically going to be, in this problem, playing with the variables given to you here to end up with fx at the end. So it's just a variable that's storing.
Why do you need it in life?
Why do we need it? Well, because the declaration of the type writer requires that, or monoid, I should say.
I'm going to be cheesy and say, why does it require that?
Yes. It's trying to find a definition of it. Where's writer? Right, writer is declared right here. Data writer A, let me zoom in. Yeah. Data writer WA equals writer AW. So this is how you instantiate a writer. Just like in normal programming languages when you have, let's say, like in Python, right, class car, right? And then the way you instantiate that is, well, you give it a certain inputs, right? So you perhaps give how many tires, the number of tires that car has, how many horsepower. These are just the two variables that you need to instantiate the data type writer with. And they're just stored in there. So this doesn't represent much in this format, but like these two variables right here describe a part about this exact writer type, data type. So yeah. And you're going to be using the same logic for right unit. So this is for left unit, right? You're going to be using the same logic for right unit. Left unit. Right, you're going to be using the same logic for right unit, but for associativity, it's going to be different. Like for when you're doing the third question of the third sub-question of the first question, the way you're going to do that is you're asked to prove associativity, right? And let's open that question. Right, so this question right here, the third one, associativity. What you want to do here is you take these two different expressions. One tactic you can use is go from this expression right here to the expression on the right side of the equal sign. But that's going to be too much work. It's going to be way too many steps. So what you want to do is arrive at a the same expression from both sides. So you're proving that they both equal to the same expression. If they equal to the same expression at the end, they must be equal to each other at the end, right?
I do this using the first method.
Oh, really? Yeah, I mean, but both methods work as long as you can show that you are indeed proving that these two expressions are equal to each other. So yeah, that's question one.
So I'm trying to work out like left unit, and I was thinking, like, for example, because if we look at bind, right,
Yeah.
for the writer, it gets kind of messy. So how would we like simplify that?
For bind? Yeah, so what you want to do, so yeah.
I can see plugging the definition for return and
Exactly.
plugging the definition for bind.
Yeah.
But then the bind is just like a lag statement.
Right.
I think it's
Right, yeah, I see it. Yeah, I just want to point out that this right here variable
Is bind.
is the infix operator of bind.
Yeah.
Yes. So what this means here, this means xm bind f, right?
Yes.
Yeah. Well, the way that you,
Bind, yeah.
yeah, bind xmf. What happens here is you just replace that one line with these three lines. But it gets messy, as you said, but like it's supposed to be like that because going from bind writer xmtf, the only step that you can take is just finally do the function of bind on the writer xmmt variable. That's going to give you 3 lines. You're going to be simplifying those 3 lines. So the way that I would suggest you go through that is replace bind, or utilize a function bind on writer, and just step by step work towards simplifying those 3 lines. So there are going to be some variables that you can get rid of, right? Without giving too many hints. But you're going to end up from 3 lines to 2 lines, and you're going to simplify those 2 lines further. And then at the end, you should end up with fx at the end.
Okay.
Yeah. Yeah. So yeah, any other questions about question 1? Yeah. Okay. Then we can progress to question 2, lambda print. Yeah. So here, we're given a language, or we're given an extension to our lambda calculus language with these expressions. But obviously, the new ones that you guys might notice are such as concat E1, E2, output E, right? And the string expression type here. And for the values that we can now have a lambda function as a value. We can have a string as a value, and we can have the unit type itself as a value. And what you're asked to do here is you're asked to provide the substitution semantics for implementing a large step relation for this extension in this language. So to erase this. Right. So yeah. So we want you guys to give the substitution semantics to do this large step relation with these extensions. So logically, what you should be thinking about is providing the axioms and the inference rules such that these extensions right here can still be applied to the large step relation function. And at the end, you should end up with a value in a string. I could give a hint here and say that you do not need to write the substitution semantics for the expression type x, right? We're just expecting 6 inference rules from you guys. And those 6 inference rules will correspond to those of these. So like the lambda function, the application string, concat output and unit.
Yes, that was actually, I would ask that we don't need one for x, right?
No, yeah, you don't want for x, because it's already given. Yeah, it doesn't also make sense. So what I can explain about this here is obviously the plus plus, right, indicator. This is just a concatenate strings. So like if you have string a plus plus b, this in our language just means that you end up with a string ab. Yeah, so don't get too hung up on that. I also want you guys to notice that in these expressions here, some of them are going to be outputting strings at the end, right? So here, the tuple that we want to end up with at the end includes a value, right, and an output string. So this output string here will only be produced by the application expression, the output expression, and the concatenate expression, right? So when you write the inference rules for these 3 types of expressions, you guys should indicate in your inference rules how the output string will be made, how that will be constructed as we evaluate these expressions.
For the other ones, we need the empty string, which is the units, right?
Yeah, so why do you need the empty string? So why is that the case? It doesn't what?
It doesn't output any strings.
Right, it doesn't output any strings when you evaluate the expression. Yeah. And another important point for this question is very similar to how Professor Chong indicated on Piazza. You need to also provide something called an environment semantics. You need to provide the inference rules for environment semantics. And this is because in the previous section, which you can access by going here, Sarp went over environment semantics, where we utilize monadic interpreters with environment semantics. So we evaluated functions utilizing something called this p variable right here, something called a row. And row indicates the environment variables. And what happens here is the whole purpose of an environment semantics is that you, instead of basically replacing expressions with values, the whole purpose of environment semantics is that, let's say you have a variable x, and in your environment semantics, indicated by a row, yeah, you have that x maps to the value 3. Yeah. So when you evaluate the variable x in this environment semantics, you will end up with the value 3. Right. Or actually, yes, the way that you guys should indicate environment semantics here is as such. The environment semantics should come before X. It's not that important, but this is the style that we are using. So what will happen here is that you provide the empty string as well. So let me ask you guys real quick. What inference rule, what axiom would we need to make sure that this works in our environment semantics? Like, let's just write the inference rule / axiom for this to work. So what are we doing here? We said in our environment, in row, we have the fact that x is mapped to the variable 3. And row is a function. So how can I indicate that row, in the function row, when we provide x as an input, we get 3 as an output? Yes?
X gives the output 3 given that P of X is equal to 3.
So how can I write that?
As an axiom, so
Yes.
we know if there's binary no
No conditions.
or condition, yeah.
Conditions, yeah.
So X
Right here?
yeah, so P of P and X maps to
No, not maps. So large steps down to?
right. So let's say P always maps to an integer or any value.
So P is a mapping function that maps variables to values.
Okay, then say V
Exactly.
and empty string.
Why empty string again?
Because this is an output.
Okay. So how do we know, how are we going to connect V now into this whole
No,
system?
Like as a side condition to say P of X is equal to V.
Exactly. Yeah. So this is the environment semantics inference rule for just a variable type, var x. And you will need,
So we will need to provide that, right?
this is just one. You do need to provide this. So because now you are defining how your variable, that a variable given to you will be evaluated with an environment semantics also provided. And you will need to provide 7 environment semantics inference rules. 2.
You said we need 6, and you said
You need 6 environment semantics for the substitution semantics. Or you need 6 inference rules / axioms for the substitution semantics. But you also need to provide inference rules and axioms for your environmental semantics, where you basically integrate row into the evaluation of your expressions.
So is it 6 or 7 or 7 overall?
You need 6 substitution semantics inference rules and 7 environment semantics
Oh, we need both.
inference rules. Yeah, you need both. Yeah,
Okay.
that was a clarification post that
You're right.
Professor Chung made on Piazza. Yeah, we could do another example if you guys wish. Or not. Not too, yes. Yeah. Cool. So that's question 2. Yeah. Do you guys have any other questions? So 6 inference rules for the semantics, or for, sorry, I'm confusing. For substitution semantics, and 7 for environmental semantics. Yeah. And we can briefly go over the last question as well on the P set.
the one in the substitution semantics will be of the form like E alone maps like
Yeah.
supposed to something, right? So like the one like we had on the left upper corner.
Say that one more time.
So like when we're writing axioms for the substitution semantics,
Yes.
it's only E that goes to something, right?
Only E.
Like only an
Exactly. Yeah, yeah.
So there's
Only
no
an
row
expression.
in front of it.
Right. Exactly. You're not going to have a row, a P, a
Mhm.
our semantics. Yeah. Exactly. And also just to make sure that everything is clear, what does the function concat do? What does concat do?
Because it evaluates E1 to a string, then E2 to a string, and then concatenates the strings basically.
Right. Right. So then what? But the thing is, when
E1 and E2 can also
E1 and E2 can also provide output strings. So when you evaluate an expression, it's going to provide a value of some sort and an output string, right?
also concatenate those, right?
Exactly. So yeah, be careful on that. One sec. So for E1, when you evaluate it, this again might produce this will produce a value, and it might or might not produce a output string. Same thing for E2. So you guys should indicate the fact that it might produce this output string as well as evaluating to these values. And if it does provide an output string, this is what the output string will be.
So
Yeah.
would you have to handle no output string differently than like
Yeah.
you have to have, is there a special case to say if it's an empty output string?
Yes.
Can you repeat that question, please?
Sure, yeah. Can you repeat that question? Oh, you mean, got it. Sorry about that.
Like the empty output strings have to be handled separately.
Yes. So the question was, do empty output strings need to be handled separately from the normal cases? The answer to that is no, because, yeah, they don't. So let's say E1 evaluates to the expression V1, S1. When I write E1 large steps down to V1 and S1, here S1 might either be an empty string, right? Or it might be the string equaling XYZ. So S1, and let's say I have a different expression called E2 that large steps down to V2 and S2. Here, S1 plus S2 can theoretically equal the empty string if S1 plus S2 can equal the empty string if both of these are also the empty string. Yeah. So this takes care of all possibilities. Yeah. Okay.
And then another quick question is, how do we specify that the value has to be a string?
How do you specify that value
Is
to be
that
string?
as a condition? Is it like on the side where V1, V2 must be strings? How would you like formulate it?
Mm-hmm.
Or is that completely wrong?
You don't need to do that, basically. You don't need to specify the fact that they're strings.
Okay.
Yeah. So in our language here, we can have a string as an expression, right?
Yeah.
And in our value types here, we can also have string as a value. So
what happens if like V1 is like an abstraction? Then you can't directly concatenate those, right?
if V1 is an abstraction like this,
Yeah, because like right now, tentatively, what I'm doing is I'm like in the inference rule at the bottom. I say that E1 like concat E1 E2 should step to like V1 plus V2 S1 plus S2. But then how would we? But that would only work if V1 and V2 are strings.
Exactly.
So do we need to specify that, and if so, how?
so for the concatenation case, you don't need to specify that, but for the application case, when you have E1 and E2, you're going to have three conditions. You're going to have three conditions in your
E1
inference.
values is something, E2 values is something, and then E1's basically going to evaluate a specific thing, and then the way that they work out is that when you combine them, they need to evaluate to a third thing.
Right. So here you
Right, okay.
yeah, you know that E1 is going to be an abstract is going to be a lambda function such as this,
Okay, yeah.
right? So that might produce its own output string. Call it S1.
Yeah.
And then E2 by itself, when value can also evaluate to output string S2. And then yes, exactly. When you, let's say, in your expression, substitute, let's say, a variable x with a value v, that will produce its own unique value, and it might also produce another output string. Call it S3, and then you do the concatenation of S1,
okay.
S2, and S3. Yeah. Cool.
Okay.
Yep.
So concat itself, that was fine.
Concat, when you do concat E1, E2, you're going to want to evaluate the expressions,
Yeah.
right?
Like,
And then just concatenate the strings. Yeah.
okay.
Yeah.
Okay.
Yeah. So to answer your question, for concat, you don't need to worry about that third case. Yeah. Yeah. And again, don't forget about your environment semantics inference rules. Yes.
Yeah.
Yeah. Where again, you indicate it like so, like px for var. Let's say when you're doing the environment semantics for p string, you just do ps, and then this should evaluate to a given string, but then a empty string, right? And then you can have p e1 e2, p output e. All those rules need to be defined.
So how are those different than these ones? Is it just you have, so first of all you have the row in front of it, right? So it's like row, comma,
Yeah.
the thing, and then it steps to, but it steps to the exact same.
So like the first 6 rules for the environment semantics.
They're going to be very similar. They're going to be very similar, but careful about the expression type with the abstraction.
Okay.
Yeah, with the lambda calculus, because yeah, for that, that's going to get a bit messy.
Because X is going to map to a certain thing.
Exactly. Yeah.
Okay.
Yeah. Awesome. And then for the coding question.
But like for the other 5, that's not the protection. It's basically the exact same thing with the moving.
Yeah, yeah.
Okay.
Mm-hmm.
Yes, for the coding question.
Yes. Nice. So yeah, for the third question, you need to obviously install Haskell on your computer. The directions are given. Yeah, once you have those, you're given the library for the homework, and then yeah, you start working on eval.hs. Let's actually just open that real quick, just to demonstrate it. Did you start on the coding question yet?
I've like installed the library and everything. I
Got it.
just opened the code.
Can you run Haskell eval.hs? Yeah. Let me unplug this for a sec. Mm-hmm.
Yes, it works.
Cool. Okay,
It's
cool.
so high.
Yes, it should say oh hi. Then okay, I don't need to run it on my computer. Okay. Yeah. So yeah, once you run Haskell eval.hs, it should print oh hi. If it doesn't, then there's something wrong probably with your setup. Yeah. And yeah, so let's open the code. No, I don't want to open it in Visual Studio. Cool. Let me zoom in. Okay. Yeah, so.
Can you go one more?
Sure,
Say one more time?
for sure. Zoom in one more time. Yeah,
Perfect.
yes. So this right here will look very similar to you guys from OCaml. This is how we define the expression, or the expression type, right? You're gonna have multiple types such as like the lambda function, application. String literal is just the string itself, like S. The output function, the concatenation function, the unit, yes. And likewise for types of values that we can have. And these are all just setup code, yeah. So yeah, first you're asked to write the explanation for the code for the monad type maybe writer, right? And it needs to support 2 effects, output and failure. Yeah, so obviously you need to replace undefined. And here the types for MW return, MW bind, MW failure, output are all given to you, so don't mess with the types. In fact, these are supposed to give you guys hints. For example, for MW return, let's look at the type declaration here. So you're expecting a monoid with the variable type W, and then an A, right? So you might be like, what do you mean by A? And then at the end, where you're supposed to give a maybe writer with 2 variables inside, W and A. So here, A, like this, the A here before the last value that this function is expected to return should give you a hint in saying that MW return expects 1 input into the function, right? So there should go something probably like MW return A, MW return X, something like that, that shows the fact that, okay, MW return expects to input X, and then you will continue writing the code right here. Similarly for MW bind, the fact that we have 2 separate expressions here before our last expression maybe writer WB should give you guys a hint in saying that this expects 2 types of inputs or 2 variables of inputs. And here, especially for the third one, there's a parentheses and then an inner arrow, right? So what does this mean? This says that this is a function, right? This says that this is a function going from A. It expects, that function itself expects an input A and will produce an output maybe writer WB, right? Let's see if this looks familiar. Oh yeah, it does. It goes from A to and maybe writer WA, right? So this should give you guys a hint on how to approach this. And for failure, what you're asked to provide is a very simple code, which I won't reveal. But yeah, likewise for output.
So this is for part 2, right?
This is for part 2, yeah.
How about part 1?
This is part 1. Yes,
So basically, we need to like first define the data for maybe write the WA.
exactly.
And then write an instance of it. It's
Exactly.
gonna be a monoid to a monad, maybe write it. But like, I keep getting some weird errors that I don't really understand. Although, like, isn't it gonna be very similar to the definition of maybe, like a combination of the definitions from maybe and write it from
Yes,
C, right?
yes.
So,
So yes, so you definitely do want to utilize the maybe type in writing the explanation for maybe writer. Because what is maybe writer at the end? Right, so what's the whole purpose of maybe writer? What does the homework, how do you say? Right, it's not exactly a writer monad, but it's close. So it should be a combination of the maybe monad to encode failure.
that's why its definition should be a combination of them too.
Exactly.
When I try to do that, I got weird stuff.
Really?
What's the error that you get?
Yeah, what is the error that you get?
For example, like, can you, like in the PSET, can you go back to the definition of maybe?
For sure.
No, like in the PSET.
Oh, in the PSET. Sorry about that.
Nothing.
You mean like right here?
Yeah, like a little below that. Yeah,
Yeah,
over
okay,
here.
yeah.
So for the maybe writer, I tried to do the same thing,
Mm-hmm.
saying nothing, mid,
Yeah.
then just
Got it.
maybe writer.
Got it. Yeah, that's not how you. Yeah.
Something bad going on.
Yeah, you should not approach it that way. So the way that you should approach it is by using the maybe monoid inside the function. So you should not have, yeah, your
So
code should not
I
look
assume
like
that
this.
Maybe function is already defined.
You will be utilizing the maybe keyword in your constructor for the maybe writer data type. So it will go something like maybe writer, and in parentheses maybe, right? So you
And then maybe right, and then I can also use writer as well, right?
a tuple, not a writer. So yeah, you need to at the beginning indicate the fact that yes, what your constructor is a maybe writer. So it'll go something like maybe writer, and then you need to utilize the maybe data type inside the maybe writer constructor.
Why did I also need to use a
Yeah.
writer data type? Both of them.
No, just maybe writer and then maybe. Why are we using the maybe data type?
Why is it not on the outside?
It's a better way of
Like,
expressing this condition right
intuitively,
here.
I'm thinking like either the writer could be nothing, or you can have a writer.
It may be writer,
Okay, sure. You have a writer.
Yeah.
You can have nothing or maybe writer.
yes.
In which case, I would think I would do like maybe writer, but that's
Mhm.
not right. I
N-
guess
That's-
No,
I was thinking
it needs
about
to be maybe writer, maybe,
Right.
actually.
So why is that intuitively? Because
Yeah.
I just explained my intuition for
Mhm.
why it should be.
Right. So if we go to the definition of a maybe writer here, where it says to encode failure, the way that one encodes failure in a maybe writer is you still need to have a maybe writer type instantiated as a maybe writer. But then what comes after that maybe writer could just be equal to nothing. But that indicates that that value that you have there is still something of type maybe writer.
Then why is it wrong to say maybe writer WA is equal to maybe, and then in parentheses writer AV?
Maybe.
Because it's either going to be a writer or nothing.
Okay.
No, it's not going to be a writer. It's going to be a maybe writer. There's an important
Yeah, that's
distinction
for,
right
like,
there.
A maybe writer is either a writer or nothing, right?
A maybe writer is either a maybe writer or nothing. Do not declare writer by itself anywhere here. In this case, there's a distinction between the maybe writer Haskell data type and a writer Haskell data type. The writer Haskell data type has no option for failure.
But,
But,
like,
yeah.
can't you like amend it by adding a maybe in front? Like,
No, yeah, that's not the answer that we expect. The short answer.
I guess
Yeah.
that kind of makes sense. Is it because like if something inside the maybe writer, like A or W,
Breaks.
if that's nothing, then you want it to handle that.
Yes.
If you put the maybe on the outside, then it only looks at if the entire
Nothing.
Is nothing.
Exactly.
It's not exactly.
That's exactly, yeah.
Okay.
You're encapsulating inside the maybe writer data type rather than the entire data type, yeah.
And we only need to do the maybe on the A. Does that sound possibly like?
So-
I guess intuitively, what is W? W is the writer itself, like the writer, or it's a generic monoid, right?
Mhm.
So that we don't have to worry about whether or not
No.
something, right? Okay.
Should we do the
But-
maybe on the entire?
No. So you're both right in that you should do the maybe on the entire tuple, actually.
Oh.
Because the entire tuple makes up the maybe writer.
Okay.
So it's not just the A. However, what you said about W being a monoid and whatnot, and that being the whole idea behind the monoid, behind the maybe writer monoid is correct. But yes, you should definitely have maybe on encapsulated the tuple with the two variables. Yeah. Yeah.
That makes sense.
Mm-hmm. And you will, and just a quick question. What reminds you guys of this from OCaml? Data may be A, nothing just A.
Option.
The option, right? Yeah.
Hmm.
Yeah. So you can have like apostrophe A option that can either be equal to none or
None, yeah.
none, or apostrophe A option, right? So that takes care of the case where it can be equal to null. This is similar to how in Java, all data types are the subclasses of the super type class object, exactly. And all objects can either be null or the object itself, exactly. Yeah. And again, you're asked to implement the bind function right here, indicated by this denotation. And where you have to do that is, I believe, here somewhere. Yeah, eval. Yeah, or you need to write the code for eval. Yeah.
How do we test our code?
How do you test your code? Are you given test cases by any chance?
No, I think because I'm just looking at it right now, and it says that you guys don't use the main function to grade, but the main
No.
function only prints out oh hi, and then it says you're welcome to change the main function as much as you like.
Mm-hmm.
But
Yeah, I believe we make use of the functions themselves, not the main function, but we take the code that you wrote piece by piece.
okay.
Yeah,
Oh, I guess it. If it doesn't work, then it's probably going to give an error.
exactly.
But it won't
Yeah.
actually. But there are no like test cases. Right?
Yeah,
So
I
if you
would
compile
sug-
correctly, that's probably fine.
I don't want to give a 100%
Yeah, that makes
guarantee on
sense,
that, but
that makes
definitely do write your test case if you're not feeling
sense.
comfortable.
Cool.
Yeah, yeah.
So, you know how after we define data type, we instantiate it with like instant monoid W. So
Mhm.
like, for example, in the monad for the writer case, we
Mhm.
first do data and then instance, write an instance of it. For this question, we're not supposed to write an instance in part A, only say data is equal to something.
In part A, you're just writing the definition for the maybe writer.
Okay, so like there won't be a second line starting with
No,
instance,
no,
right?
no, no.
That's gonna be in part two.
Yeah, that's going to be, I believe, part 2. Yeah. So yeah, for part 2, the hardest question is definitely going to be MW bind. Because here you're going to be matching what maybe writer can be, or the monoid inside the maybe writer can be. You're going to be matching it based on, is it equal to nothing, or is it equal to just the tuple, right, AW? And then you will go cases by that. Yeah, so these should be all one-liners right here.
And part one, isn't that a one-liner as well? then?
Yes.
Wait, but like, if I say maybe writer WA is equal to maybe AW, how do I specify that W is a monoid? You don't really have to do it until you're filling.
For this, you mean?
Yeah, if I say that's maybe AW,
Mm-hmm.
do I really have to specify that W is a monoid until I make an instance of it?
No, you don't need to insert, no, because so this coding environment, Haskell, already knows about the data type maybe, right? It already knows about the data type maybe. So it knows what you're going to give it if you give it properly, which is a tuple with 2 variables inside. It knows what it corresponds to.
So saying maybe AW is enough then? In that case, like you don't have to specify what W is?
No, you don't need to specify what W is.
Okay.
Yeah. Mm-hmm.
I'm happy with that.
Yeah. Yeah, so yeah, that's the coding piece set in a nutshell. Yeah. Do you guys have any other questions about anything that we've covered in this class so far? Because we can go over the lecture notes and section notes together. Yeah, like for the final exam or something. Because for the final exam,
It is, right?
it is cumulative, but I believe there will be more questions from the second half of the semester than the first half.
And it's 3 hours long, right? So it's.
I believe so.
Multiple choice questions?
Is that it?
I'm not sure, actually. Yeah, I didn't ask Professor Chung yet. If you see this, Professor Chung. But I believe, if I remember last year, it was somewhere around that number. Yeah, and it was 3 hours. But again, just like the midterm, it wasn't
Yeah.
that stressful. And that definitely the material that you need to do the exam is given to you in the appendix, right? So I want to ask you guys a question, like how much did you guys find yourself utilizing external materials? By external, I mean like stuff other than the appendix given to you during the midterm.
Oh, I did look at the lecture notes.
From time to time, right?
Yeah.
But like
Yeah,
not that much.
Okay, but most of the appendix was very helpful.
Exactly.
So that's good, yeah.
Yeah, so yeah, the final will be very similar to that.
It's going to be a multiple choice exam again?
Yes,
It's gonna be
I believe
short
so.
again?
Is it going to be so short? For you, we will give 10 extra questions.
I guess, because like when you have only 15 questions, you do one stupid mistake. That's
Right,
like
exactly. That's the one
15
thing.
of your whole exam.
Yeah, yeah,
It's not nice.
yeah. Awesome. Do you guys have any other questions? No? Okay, well, we can end the section here. Thank you guys so much for tuning in. Take care. Bye-bye.